In this lesson, we will continue our exploration of stoichiometry. Today we're going to learn about finding the limiting reactant and about finding a theoretical yield. But first, let's look at the kind of problem we set up yesterday. So the homework problem says that we're starting with 2.50 grams of lead 2 nitrate, an excess of potassium iodide, and it asks you how much lead 2 iodide will be produced. So we're going from one chemical species to another in this question. We're going from lead 2 nitrate to potassium iodide. Lead 2 nitrate to lead 2 iodide. So we have to have a balanced equation. We need a balanced equation because we need a molar ratio. Molar ratios have to come from balanced equations, from the coefficients in a balanced equation. So I'm going to write that balanced equation first. Lead 2 nitrate. Lead's elemental symbol is Pb. Lead 2 means it has a 2+ charge. Nitrate is NO3. Nitrate has a 1 negative charge, and so I'm going to need 2 nitrates for every lead in order to charge balance this formula. And I'll show 2 nitrates like that. Lead 2 nitrate, all nitrate salts, all nitrate compounds are always soluble, so we're going to say that's aqueous. We're reacting it with an excess of potassium iodide. That's K for potassium and iodide. Potassium has a 1+ charge and iodine has a 1 negative charge, so 1 to 1 is the correct ratio. That's balanced. And that's aqueous. Iodines are almost always soluble. There's no exception to the solubility for iodine when bonded with potassium. And further, group 1 metal salts, or group 1 salts with group 1 metals in them, are always soluble. So this is aqueous for 2 different reasons in the solubility rules. Now, since I have 2 ionic compounds here, you could call them two-part compounds, the most likely kind of reaction we're going to have is double replacement. And in that case, then the front part of this compound is going to join up with the back of this. And that's the lead iodide we're asking about, or we're asked about in the problem, how much of this we're going to make. And then the front part of this goes with the back part of this, and front parts stay front parts, so it's potassium in the front and nitrate second. The subscript 3 travels because it's part of a polyatomic ion. This subscript 2 does not travel because it's not part of the polyatomic ion. Alright, so we need to balance these formulas, but first we want to find their physical states to make sure we have a driving force. Of course, the way the question is worded, you know there's a driving force, but nevertheless, that's the way I teach it. And iodide compounds, we said, are mostly soluble with some exceptions, and lead 2 is one of the exceptions. So this is going to be solid, not aqueous. Nitrate compounds and group 1 metal salts are always aqueous. This are always soluble. So since this is happening in water, this is aqueous. All right, we've got lead 2 has a 2+ charge. If it starts out as lead 2 over here, and I don't tell you it changes, you have to assume this is going to be lead 2 over here. At least that's the reasonable assumption to make. And since this is a 2+ charge and iodide has a 1 negative charge, I need 2 of these iodides to balance out or charge balance the formula with a 2+ charged lead. Potassium is 1+, nitrate's 1 negative. That's already balanced the way it's written. Now, we need to write an atom inventory to make sure that we have a balanced equation. So we're going to list all of our elements, Pb, N, O, K, and I. We're going to make a kind of grid to keep everything nice and neat, keep up with everything. A kind of a mini spreadsheet here. And we're going to count all the atoms we have in the equation. We have 1 lead here. This 2 outside this parentheses means I'm multiplying the nitrate by 2. Since each nitrate has 1 nitrogen, the 2 means I have 2 nitrogens, and 2 times 3 are 6 oxygens. I have 1 each of potassium and iodide. On the other side over here, I've got 1 lead. I've got 1 nitrogen. I've got 3 oxygens, 1 potassium, 2 iodides. We want to save oxygen for last. Let's start with the nitrogen. I've got 2 on the left. To get 2 on the right, I need a coefficient 2 in front of the species that contains the nitrogen. We can't change the formula. You can't stick more subscripts or even coefficients inside this formula. Once it's balanced, you leave it alone. So 2 outside here means it's 2 of everything in that formula. So I'm going to change the number of potassiums and nitrogens and oxygens. I have 2 potassiums now, I have 2 nitrogens now, and I have 6 oxygens. Alright, so the nitrogens are balanced, oxygen is balanced. Potassium and iodide are not balanced. So in order to have 2 potassiums, I'm going to put a coefficient in front of this species. That's going to change the number of everything in there, in the sense that I'll now have a changed number of potassium and iodides. 2 times 1 is 2, 2 times this 1 is 2, and everything's balanced. Now then, this is just the beginning. This is what we have to have in order to write stoichiometry, because stoichiometry is the math and chemistry that requires a balanced chemical equation. So we started with 2.50 grams of lead-2 nitrate. That's going to be where we start with the stoichiometry. 2.50 grams of lead-2 nitrate. And we're going to put our starting amounts over 1. For most of the kind of problems that we're going to do in here, putting your starting amounts over 1 will always work. In order to do stoichiometry, we've got to first get our starting amounts into moles. Everything has to go through Moleville, I like to call it, okay? So we're going to have to find the molar mass to convert this mass into moles. And for molar mass, we're going to add up the atomic masses of all the elements in this formula. Now, even though it doesn't really apply here, I want to make sure I'm really clear about something. When you're adding up the atomic masses, you don't even consider these coefficients. It's only the atomic mass, total atomic mass for the formula, not for the total amount in the equation. Okay? So when you're figuring out molar mass, you're going to ignore the coefficients. That makes sense? So if I were finding the molar mass of potassium iodide, I would have 1 potassium and 1 iodide, not 2 of each. Alright? Just a word of warning, because it will come up probably later in this lesson. Alright, so looking at the periodic table, atomic masses are listed at the bottom of each of the squares for each of the elemental symbols. So the atomic mass of lead is 207.2. The atomic mass of nitrogen is 14.01. And oxygen is 16.00. In the formula, I have 1 lead, I have 2 nitrogens, and I have 3 times 2 or 6 oxygens. We could add them all up. I could add this once and add this twice and add this 6 times. But with the more complex formulas, this actually makes it easier. Yes?
So if you're doing the molar mass for potassium iodide, you would completely ignore the coefficient and just add the mass of potassium iodide?
Yes. Okay, so the question is, well, I think I answered that already. If I were finding the molar mass of potassium iodide, I would add the atomic mass of potassium to the atomic mass of iodine 1 time to get the molar mass. Okay? All right. So this is 207.2. This is 28.02. And 16.00 times 6, I believe, comes out to be 96.00. Adding all these together, I get a 2 here and a 2 here. And that comes out to be 11, carry 1, 331.22. And this is going to be grams of lead-2 nitrate. Reminder from Unit 1, whenever you have empty slots to the right, like this, the resulting digits are insignificant. So we have to round this answer off. So this is 331.2 grams of lead-2 nitrate. And for me in this class, I mean, technically that's actually the molar mass. But in this class, because of the way that I try to teach you to write conversion units, I want you to always write that this is equal to 1 mole. It's just a reminder, okay? If you take AP Chemistry, You could ignore this step because it'll be so solid in your brain you probably won't forget it, which is the point. Okay? You can afford to take shortcuts after you've practiced without the shortcuts over and over again. All right? All right, so what we want to do now is to build a conversion unit from this equality statement. Now, just so you know, I've said this a number of times, I want to say it again, all conversion units are built from, whether you write them or not, they're actually built from equality statements. There have to be two things that are equal in order to write a conversion unit. We're going to actually do that here, okay, to remind you of that process. So we want to make sure we put grams of lead-2 nitrate on the bottom here so we can cancel that. So this side of the equality statement goes on the bottom of this conversion unit. And then the other side of the equality statement goes on the top. And just a kind of a reminder, whenever I put two things that are equal, one side of the equality on the top, one side of the equality on the top, whether I flip it or it's like this fraction is actually has a value of the number 1. Okay? Because the two things are equal, you put two things that are equal, one on top, one on the bottom, it equals 1. All right, now, so what this does is, when we're multiplying the starting amount by this new fraction, we're changing the way it's measured, not changing the amount. Okay? Now, the next step actually changes to a new species, and that's called the molar ratio. From the balanced chemical equation, the coefficients can represent moles. They can represent any multiple of one formula unit, and a mole is a counting number. So we're actually multiplying by 6.02 times 10 to the 23rd every time we write this molar ratio. So 1 mole of lead nitrate, we're going to put that on the bottom because it allows me to cancel the moles here. Let me go ahead and do this in order. We should cancel as you go. One mole, PbNO3, 2, and then we're trying to get to, in the question, lead-2 iodide. That's this. So I have 1 mole, a coefficient of 1 here, 1 mole of lead-2 iodide on the top. Now, to have a measurable amount of lead iodide, because you can't measure moles, it's a counting number, and we can't count all the formula units of lead-2 iodide. It's just impossible. We have to have a measurable amount, and that's what we need mass for. So we've got to have another molar mass calculation for lead-2 iodide. I don't know why I didn't put a P after that B over there. I mean, I don't know why I didn't put a B after that P here. I will do it here, PB. In the formula, I have 1 lead, and I have 2 iodides. The atomic mass of iodine is 126.90, 207.2, and 126.90 times 2 is 253.80. 253.80. Add those together, you get 461.00. And be careful when you're using a calculator if you're adding these numbers together, because it'll give you 461, and you won't recognize, oh, there's supposed to be 2 zeros there. You've got to know that. But we do have an empty slot here. We still have to round that off. Now that's going to be grams of potassium, lead-2 iodide, grams of lead-2 iodide. But since I've got to round that off, show an arrow to show that I'm rounding off. An arrow is the only appropriate operator that shows you're rounding off in a class like this. So it's 61.0 grams of lead-2 iodide, and it equals 1 mole of lead-2 iodide. Okay? Now that I have an equality statement, I have the building blocks, if you will, of a molar ratio up here. I'm going to put moles on the bottom this time so that I can cancel the moles on the top I have here. And I'm going to put the mass on the top, and that's going to leave me with mass, which is what I want to have. Canceling as I go. I forgot to do that last time. and 3.47, 977, 05314 grams of lead to iodide. And we're going to round off. You're going to look at the measured and calculated numbers of the problem and round off to the measured or calculated number that has the least digits. We're going to ignore the ones or other counting numbers because those are infinitely significant. Okay? That means you could have as many zeros after a decimal place as you could possibly imagine and more, and it's still going to be accurate. So we can ignore those because they don't really matter. We need the least digits, not the most digits. So this number is a measured number, and it has 3 digits that are significant. This one has 4. This one has 4. So this has the least digits. We want our final answer to have the same number of digits. That's the rule for multiplication and division. 1, 2, 3 significant digits. Underline everything that follows. Draw an arrow because that's the only appropriate way to show an operator. That's the only appropriate operator that shows rounding. And we get 3.48 grams of lead to iodide. All right? In this case, the goal is a bit different than in the last problem, the problem I assigned for homework and we just went over. In this case, we're trying to find what's called a limiting reactant. Let me explain theoretically what a limiting reactant is. Yesterday I played part of a song for you. We talked about making cookies. Okay? When you're making cookies, let's just say your recipe calls for 2 cups of sugar and 2 cups of flour, among other things, and you only have 1 cup of flour. What does that tell you about the number of cookies you're going to end up making? Everything's going to be cut in half. Because you need 2 cups of flour, you only have 1, you have to cut all the parts of your recipe in half. Okay? Well, that makes the flour the limiting reactant when you're making those cookies. All right? So a limiting reactant works the same way. If I am reacting chemical A with chemical B, and I need, let's see, 2 of these for every 3 of these, but I only have 2 of these for every 2 of these, there's not enough of this to completely react with all of this. So that makes this the limiting reactant. Okay? The reaction stops when this part runs out. Just like the flour stopped the making of cookies. The flour is a limiting reactant. Okay, that's what we're trying to figure out. What is the limiting reactant? And again, we need stoichiometry to do it. So we need since we're going from one species, aluminum sulfate, to another species, strontium bromide, we're going to need a balanced equation. So we're starting with aluminum and sulfate. Aluminum has a 3+ charge. Sulfate has a 2- charge, so I need 2 aluminums and 3 sulfates to have a balanced formula. Okay? And we're going to start with 2 grams of this. So we're going to put our starting amounts over 1. Okay? In order to find an amount of the strontium bromide, because in this case I've got to go from this to this, from aluminum sulfate to strontium bromide to find a limiting reactant. Okay, I've got to go through Molesville, so I've got to convert to moles. I could reasonably go from strontium bromide to aluminum sulfate. Doesn't matter which one you start with. They're both going to give you the same answer in the long run. Okay, but let's find a molar mass for aluminum sulfate so that we can convert it into moles. All right, so we're going to add up all of our atomic masses of all the atoms in the formula. Aluminum's atomic mass on the periodic table we use is 26.98. Sulfur's atomic mass is 32.06. And oxygen is 16.00. No, I did them in first period. So we got 2 aluminums in the formula. We've got 3 sulfurs. There's 3 outside this parentheses. Means I have 3 of everything inside. 3 sulfates, and each sulfate has 1 sulfur. So if I have 3 sulfates, I have 3 sulfurs. And I have 12 oxygens. What? Aluminum has a 3 plus charge. Sulfate has a 2 negative charge. To charge balance this formula, I need 2 aluminums and 3 sulfates. So this times 2 is going to be 53.96. This times 3 is 96.18. This times 12 is 192.00. Now if you put this in the calculator, 16.00 times 12, it won't give you those 2 zeros. You have to be a little smarter than your calculator and know that those zeros belong there. Add them together, we get 342.14. Okay, and you have to know, your calculator won't tell you this, have to know that this is grams of aluminum sulfate. And for this class, you have to always write that that's equal to 1 mole of aluminum sulfate. Now when you get to AP Chemistry, if you take AP Chemistry, and I think that a lot of you are, you can skip this step right here. Okay, once you get the mass, that's all you need. In fact, you can probably do the calculation in your calculator, won't have to write it down, but you're going to be so used to the process that it's going to be automatic for you. And that's my goal here. It's become so automatic because it's just so important to all the kind of chemistry we do and so much of what we do that, you won't have to worry about it. AP Chemistry, you can put it in the calculator, you're done. You don't have to worry about it. Okay? All right. So we have an equality statement here now. And from this equality statement, we can build a conversion unit. Now, conversion units are often built without equality statements. But that doesn't mean that it isn't there. There is an equality statement for every conversion unit. The only reason you can write a conversion unit is because 2 things are equal. And you put 2 things equal to each other, one side of the equality on the top, one side of the equality on the bottom. The fraction itself equals 1. Okay, the value of this fraction we're going to write is going to equal to 1. So when we multiply, we're not changing the amount of stuff, we're changing the way we measure it. That's all we're doing. So we want to put the mass here that we calculated on the bottom, 342.14 grams of aluminum sulfate. And then we're going to put the 1 mole on the top. And cancel as we go along so we can kind of keep up with where we are. All right, now that we're into moles, we're at Moleville. We're ready to convert from one chemical species to another, and that's what we need a balanced equation for. Hey, I haven't balanced an equation. So you can do it this way. You can wait to this point to balance your equation. Let's do that. Let's see, we got aluminum sulfate. And it's aqueous. And we've got strontium bromide. And it's aqueous. Strontium bromide is written SrBr2 because strontium is 2 plus, bromine is 1 negative. I need 2 bromines to charge balance the strontium. Okay, this is going to be a double replacement reaction. Here's how you know. This is an ionic compound. You can recognize it as an ionic compound because there's a polyatomic ion in the formula. This is also an ionic compound, and you can recognize this as being ionic because you have a metal bonded with a nonmetal. Metals are on the left side of the periodic table, over here. Nonmetals are over here. Okay. So these are 2 ionic compounds. If I have 2 ionic compounds reacting together, if there's going to be a reaction, the front and back parts are going to switch around. The front part of this goes with the back part of this, aluminum and bromine. The front of this goes with the back part of this, strontium and sulfate. Now the way I taught you to do this in the last unit was you wanted to figure out, before you balance the formulas, you wanted to figure out what physical states you have, because if you don't have a driving force, there's no reason to go any further. Now, this question implies that there is a driving force because we said we're going to have a product. But let's do it that way anyway. Let's figure out our physical states. Aluminum and bromine. Bromide compounds, according to the solubility rules, are usually soluble. There are some exceptions, but aluminum bonded to bromine is not one of those exceptions. So this is going to be aqueous. Sulfate compounds. Most sulfate compounds are soluble. There are some exceptions. Strontium is one of the exceptions. So if it's mostly soluble, but not when it's bonded to strontium, then it must be insoluble, and therefore it's going to precipitate in the reaction. This is going to be a solid. Okay? Now we're ready to balance the formulas. Aluminum is 3 plus, bromine 1 negative. To charge balance this formula, we need 3 bromines. And strontium is 2 plus and sulfate is 2 negative. That's charge balanced already as written. So now we're ready to balance the equation. Once you balance the formulas like this, leave them alone. Don't stick any numbers in the formula. Only use coefficients to balance it. Let's first count all of our elements using an atom inventory. Here's aluminum, sulfur, oxygen, strontium, and bromine. We're counting all the atoms in the equation. We're listing all the atoms in the equation. Now we're going to count them. I'm going to count the ones we have on the left and the ones we have on the right. So over on this side, I've got 2 aluminums. This 3 outside the parentheses tells me I have 3 sulfates, and each sulfate has 1 sulfur, so that's 3 sulfurs I have, and 12 oxygens I have. I have 1 strontium and 2 bromines. Over on this side, I've got 1 aluminum, got 1 sulfur, 4 oxygens, 1 strontium, 3 bromines. Now, you can see that's not balanced. So something's happening between this side and this side, and as we've listed it so far, we don't have the same number of atoms on both sides. Now that violates the law of conservation of matter, and we can't do that. So we have to, because we know everything's made of atoms, we're going to get everything balanced on both sides for the number of atoms. If we have the same number of atoms on both sides, we'll have it mass balanced, and we won't be violating the law of conservation of mass anymore. So since I have 2 aluminums right now listed on this side, I've got to write 2 aluminums on this side, and the only way to reasonably do that is to use coefficients. So I'll put a coefficient 3 there, and because this 3 applies to the entire formula, we're now changing the number of aluminums and bromines. So now I have 3 aluminums and 3 times, I'm sorry, I should put a 2 here, not 3. 2 aluminums and 2 times 3 are 6 bromines. Okay? All right, we're going to go to sulfur next. Sulfur, I've got 3 on the left. I have currently 1 on the right, so I need to put a coefficient of 3 in front of the species that contains the sulfur. That's going to change the number of strontiums and sulfurs and oxygens. That's going to give me 3 strontiums. It's going to give me 3 sulfurs, and 3 times 4 are 12 oxygens. All right, so we've got aluminum, sulfur, oxygen, all balanced. Let's go to strontium. 3 on the right. To get 3 on the left, I put a 3 here. Changes the number of strontiums and bromines. And now I have 3 strontiums and 6 bromines. And the equation's balanced. So those coefficients are going to be very important because those are what we're going to use in this molar ratio step. I want to have the same units of species that I have right here in the top of this step. I want to have that same number of units of species down here, and I get those from the balanced equation. The coefficients in front of these species can be one of these formula units, or it can be a mole of those formula units. Okay, any multiple of those still keeps the ratio right. So I have 1 aluminum sulfate. We can say that's 1 mole of aluminum sulfate. And we're trying to find the solid here. No, we're trying to go to the other species, the other reactant here. So we've got 3 of those. So we can say that's 3 moles of strontium bromide. Okay? And canceling as I go. Now, we can't measure moles. Moles are counting numbers. So we've got to convert moles into mass. So we need another molar mass calculation for strontium bromide. Strontium is 87.62. I have one of those, 87.62. Bromine's atomic mass is 79.90. And in the formula, I have two of those. Now, this is that situation I mentioned earlier, where I've got a coefficient out in front. You don't use that coefficient at all to figure out the molar mass. You only use it for the molar ratio. Okay, so we're ignoring this 3 when we're figuring out molar mass. Molar mass is only for the number of atoms in the formula itself, not for the number of formulas. Okay, that's why I have a 1 and 2 here, 1 and 2. So 2 times this 79.90 is 159.80. And again, you have to be careful if you put it in your calculator. Got to take note of that 0. And we add those together, we get 247.42. And that's the grams of strontium bromide that is in 1 mole of strontium bromide. This equality statement then gives me what I need to write a conversion unit. I'm going to put the moles on the bottom this time because I want to cancel these moles. Please remember that you're going to put on the bottom of every next fraction what is on the top in units and species anyway, what is on the top of the previous step. I'm pleading with you to remember that. And even though I plead with you, somebody's going to get it wrong on the test. It's going to just break my heart. Because I want you to get it right. I want you to ace the test. That should be a 2 here. Sure. Alright, cancel as we go. And I can see that I've successfully set everything up so that all the units and species are canceled except the one I am looking for in the problem. I'm looking for the mass of strontium bromide. So I'm ready to do the math now.
What is that little thing after the segment? Oh, is that the decimal? Oh, this is
Right here? Yeah, it's supposed to be a decimal. Alright, so I get 4.33892 558 602, and that's grams of strontium bromide because I've canceled all the units and species except that. And to round this off to the correct number of significant digits of the measured numbers like this one and the calculated numbers like this one and this one, this number has the least digits. That's how many significant digits I want in the final answer. 1, 2, 3 significant digits, and underline everything else. Draw an arrow because that's the only accepted thing we use in this class to show a rounding off, and round it off to 4.34 grams of strontium bromide. While it's not going to be counted against you, if you don't do it, it'd be appreciated if you put a rectangle around your final answer to help me find it in the midst of all this calculation. Okay? Now, this is not the end of the problem because this doesn't tell us what the limiting reactant is, and that was the question. But this is going to give us, help us to figure it out. So the problem says we started with 2 grams of aluminum sulfate and 2 grams of strontium bromide. What this calculation tells me is if I have 2 grams of aluminum sulfate, I must have 4.34 grams of strontium bromide to completely react with it. I don't have that much. Okay? So, like our flour, strontium bromide runs out before I can use up all of the aluminum sulfate. Okay? This is strontium bromide then is the limiting reactant. That, those 3 dots in a triangle like that is a symbol for therefore. earlier, I said that it doesn't matter which one of the two reactants we start with. Alright, I want you to prove it to yourself. I want you to do this whole calculation over again, only this time, instead of starting with aluminum sulfate, I want you to start with the strontium bromide. 2 grams of strontium bromide, do the same math, and find how much product, or how much of the other reaction you're going to get. Let's take a look at this. Starting with 2 grams of strontium bromide, we're going to build a conversion unit called a molar mass conversion unit. And you can see that we can cancel out grams of strontium bromide. Here's moles of strontium bromide, so now we've got the molar ratio. In this case now, the number of moles of strontium bromide is 3 in the balanced equation. That's where we get that 3 from. The number of moles of aluminum sulfate is 1 in the balanced equation. That's where we get that 1. And then the moles of aluminum sulfate can cancel, and we're left, and our final units of species is grams of aluminum sulfate. So when we do the math then, we get 0.922 grams of aluminum sulfate. Now what does that mean? Since we actually had 2 grams of aluminum sulfate, this number is the amount of aluminum sulfate that's going to be used up in the reaction to completely react with all this strontium bromide, So there's going to be plenty of aluminum sulfate left over. If we're only using up less than a gram, there's got to be more than a gram left. And so that makes that the excess reactant. So therefore, aluminum sulfate is the excess reactant. Since we only have 0.9 grams of aluminum sulfate being used up, there's more than a gram of aluminum sulfate left over because we started with 2 grams. Therefore, aluminum sulfate is the excess reactant, and that means that strontium bromide is the limiting reactant. So either way you do this mass-to-mass calculation, determining the limiting reactant, and it doesn't matter whether you start with strontium bromide or you start with aluminum sulfate, you're going to get the same answer. All right, so what I want you to do next now that we've identified the limiting reactant, we know that strontium bromide is the limiting reactant, we know we're starting with 2 grams of strontium bromide. I want to have you help me calculate the mass of solid product that will be produced. Okay, the mass of solid product that will be produced. We're going to start with that same 2 grams of strontium bromide. That's the limiting reactant. The species here, strontium bromide, is the limiting reactant. And the amount of limiting reactant we are starting with is 2 grams. Put that over 1. We're going to use the same conversion here that we started with in the previous problem. 1 mole of strontium bromide on the top. The molar mass of it on the bottom, 247.42 grams of strontium bromide. Cancel as we go. We're going to do the molar ratio now. The 3 moles of strontium bromide stays the same. We need to look at the balanced chemical equation and figure out how many moles of the solid product that we're going to need. And so here's the solid product, okay, strontium sulfate. There's 3 moles of that as well. So we're going to put 3 moles of strontium sulfate on the top. And then we have to do a molar mass calculation and determine the amount or the molar mass of strontium sulfate. When we calculate the molar mass of strontium sulfate, we'll find there's 183.68 grams of strontium sulfate for every 1 mole, excuse me, for every 1 mole of strontium sulfate. So we want moles on the bottom, so the 1 mole of strontium sulfate goes in the bottom. and the 183.68 grams of strontium sulfate goes on the top. Need to cancel as we go here, and we can see that we've set it up so that we're going to end up with some mass, because I've got grams here of strontium sulfate. We did the math. Grams of strontium sulfate. Your calculator may show fewer or perhaps even more insignificant digits. What we want to do is round it off to the correct number of significant digits. We have 3 digits in this measured number, 5 significant digits in this calculated number, 5 significant digits in this calculated number. So we want our final answer to match the number of significant digits of the measured or calculated number with the least digits. So there's 3 in this one, that's the least digits. Underline everything after the first 3 digits. Draw an arrow to show that we're rounding off. And we have 1.48 grams of strontium sulfate. That's theoretically how much strontium sulfate will be produced in this chemical reaction. Now, theoretically is there for a reason, because as we're going to find out in a later lesson, there's something called an actual yield. This is the theoretical yield. Okay? So this is the theoretical yield. In strontium sulfate. So your homework is to do another one of these problems where you're trying to find a theoretical yield. And just as in this case, you have to first identify, through this stoichiometry process, identify the limiting reactant. Once you find the limiting reactant, then you start your stoichiometry to find the theoretical yield with the amount of limiting reactant that you are given. Not the amount you calculate if that's at the end of one of those problems where you're trying to find limiting reactant, but the amount given in the problem of the limiting reactant will be the starting amount to calculate your theoretical yield.